Hello, Yuvraj sir. Hello. Hello, Yuvraj sir. Sir. Hello, sir.
Hello, sir. Is it audible?
Yes, sir. Yes, sir.
Yeah. Actually, I joined in through my sister's laptop, so that's why
Yes, sir.
it is
Yes, sir.
login ID.
That's why I could not able to.
Yeah, just now I noticed.
Yes, sir. Yes, sir. Yes, sir. Okay.
Since I was using her
I
laptop.
will make it as co-host, sir. I will make you as co-host.
Okay, sir.
Rashekar, sir.
Sir, co-station, sir.
Okay. Right, sir. Right, sir. Yeah, I have seen. Padmalata, madam. Padmalata, madam.
Sir. Sir.
Now you can read the biography of Dr. S. Yuvraj.
Okay, sir. I welcome you of IST and IST sponsored online course for millimeter wave frequencies. It's my pleasure to introduce Dr. S. Yuvraj, sir. Dr. S. is BA degree in Electronics and Communication Engineering from PSNA College of Engineering and Technology, Dindigul, India, in 2001, and MTech degree in Microwave Engineering from IIT Varanasi, India, in 2014. He received PhD degree with the specialization in RF and Microwave Engineering from IIT Roorkee, India. Currently, he is working as an assistant professor at NIT Andhra Pradesh, Tadepalligudem, India. His current research interests include design of millimeter terahertz wave vacuum electronic devices, the design of microwave millimeter wave circuits and antennas. With this brief introduction, I hand over to Dr. Yuvraj, sir. Sir, please continue.
Hello.
Hello, sir. So, shall I start?
Yes, sir. Yuvraj, sir, you can start your session.
Okay, sir. So, my voice is audible, na? Clear?
Yes, sir. It's very clear.
Okay, sir. Thank you. So, I hope the slide is visible, huh?
Yes, sir. It is visible.
Okay, so today's topic of discussion is
full screen. You can go for the full screen mode, sir. It's visible.
All right.
Yes,
is that fine? Okay, so everything looks fine. Okay. So yes, the topics of today's discussion is recent trends in millimeter and terahertz wave vacuum electron beam devices. So in this lecture, I will cover some of my works carried out at IIT Roorkee during my PhD time, and I will also discuss about the extension of the work which we are carrying out after that. And I worked under the guidance of Professor M.V. Karthikeyan at IIT Roorkee. So this is a brief introduction. So I have divided this presentation in such a way that first we will discuss about what are the recent trends occurring in uh, vacuum electron devices, especially traveling wave tube amplifier, Klystron amplifier, backward wave oscillators. And we will also discuss what are the current requirements of these vacuum electron devices in high power regimes. And we will see one peculiar problem which we solved at IIT Roorkee, that is a design of multi-frequency coaxial cavity gyrotron. Then we will look into some conclusions and feature scopes. So as we all know that vacuum electron devices, so these are called as microwave tubes in generally, and they are very popular for high power applications, especially when you want heating something and when you want to heat the particles using RF source, then only these microwave tubes are very popularly used. And one of the most widely used microwave tube is, as we all know, the magnetron oscillator. So magnetron oscillator is widely used in all our home appliances. And next most popular is traveling wave tube amplifier, because this is the one thing which decides the lifetime of the satellite. So your traveling wave amplifier is the robust source that they use in a satellite communications. And as you generally see, these microwave tubes are widely dominant at high power applications, especially when you need a very large power requirements. And whereas our solid state devices like GAN based device or any other solid state device which we use in mobile circuits, they are dominating a low power regime, and they are widely used uh, at low power application, especially commercial electronics. So there is always a region of competition between them at millimeter and terahertz regime. Why? Because in millimeter and terahertz regime, especially in a range of 100 gigahertz or around 80, 90 gigahertz, the power offered by the solid state devices are very less. So yeah, so in that scenario, we need to use vacuum electron devices only, because the vacuum electron beam devices are very much efficient in delivering the power. But the problem is the fabrication of these vacuum electron devices is very difficult. You can't fabricate in a mass scale. But however, due to the advancement in the machining technology, especially occurring in nanoscale fabrications and micro fabrications, so this makes the vacuum electron devices more competitive in nature. And nowadays you can fabricate a very tiny TWTs even at 140 gigahertz, which was not feasible in 10 years before. So nowadays it is feasible. So there is a region of competition, and the vacuum electron devices nowadays not only used for heating application, they are also capturing the other applications, especially the commercial electronics like commercial communications in 5G sectors. Okay. So this is a brief introduction about microtubes and solid state devices. So the one of the most popular microtube is a traveling wave tube amplifier. Because of their robustness, they are still the champions in satellite communication, and they offer a very large bandwidth, and they are so much robust you can use it in satellites. And the current state of the arts are the Q-band TWT, that is at 42 gigahertz. They developed for 3 gigahertz bandwidth for satellite communication. Whereas for a commercial 5G wireless networks, for a backhaul network, they developed 95 gigahertz 40 watt TWT to support a capacity of 10 Gbps per square kilometer. And a D-band TWT was also developed to support a to support a capacity of 100 Gbps. Okay. So these are the current state of the arts of traveling wave tube amplifiers. And coming to the klystron amplifier, the klystron is widely used in heating application, especially in a linear accelerators. Like in India, we have RRCat indoor, where we have a linear accelerator setup where they use 5 gigahertz klystron for their RF heating. So klystron is an amplifier where you need a high gain, then you go for a klystron based amplifiers. Okay, and in klystron, the state of the arts are they are 95 gigahertz klystron that deliver output power of 2 kilowatt with an efficiency of 50%. This klystron is 95 gigahertz klystron is a sheet beam klystron because your electron beam in this case is sheet. Okay, so you have a very compact system and the efficiency also very high. And another variant of this klystron is extended interaction klystron. So what do you mean by extended interaction means? Your extended interaction means you are having the interaction region. So this is the interaction region. So if your interaction region is slightly extended, you have a very large efficiency in beam wave interaction. So which in turn increases the gain of the entire amplifier setup. So this is also one variant of normal klystron amplifier. So they are widely used at 100 gigahertz above. So a compact 220 gigahertz 9 watt continuous wave gyrotron was reported by the researchers for imaging systems. Okay, for imaging systems, they have reported this. So next is backward wave oscillator. So in backward wave oscillator, we have the interaction not only in a forward direction, but also in a backward direction. Okay, so in the backward direction, if you have the interaction in a backward direction, what is the advantage is you have both the input and output coupler at a single port. You don't need to keep a separate output port at the port 2. So you have both in the first port itself, you have both the input as well as the output. That is one advantage. And another peculiar reason why people use this backward wave interaction is they can tune the oscillator in a very fast rate. So for example, if you're operating your device at 100 gigahertz, you need it to operate for certain application at 101 or 199.5 gigahertz. So the tuning should done in a very fast scale. So for certain application, these backward wave oscillators are widely preferred, and and they are used in imaging systems, and they are also used for the diagnosis of the plasmas. So these are all about backward wave oscillator. So coming to the gyrotron, so gyrotron is one of the most popular microwave tube, that is vacuum electron device at high power regime. Means high power in the sense we need above 100 kilowatt. Okay, so above 100 kilowatt, you need a power with the pulse of 30 minutes. Okay, so this is the general requirement of all plasma heating community. Okay, so you need to have a gyrotron with a pulse that is it has to supply the power for a period of 30 minutes. Okay, so if you are operating the gyrotron, especially like 100 kilowatt for 30 minutes, your setup should be as big as possible, so that the entire heating system should be working in a perfect way. So gyrotron is one such device. Okay, and they are widely used for plasma heating applications. So in addition to the plasma heating application, the gyrotrons are also used for ionization of particles. They are used in a medical spectroscopy, and some low power gyrotrons like 20-watt gyrotron, they are used in medical spectroscopy. Medical spectroscopy means in DNP NMR experiment, to increase the sensitivity of the NMRs, they use this RF source. So the RF source are used to increase the sensitivity of the NMR. So in that case, gyrotron is one of the most preferable source. Okay, and so this figure shows the schematic of the gyrotron. So you have a magnetron injection gun, that is the source of the electron beam. Okay, and you have uh, the external magnetic system, and you have a beam tunnel region, and here is the interaction cavity where the interaction between the electron beam and RF take place, and the energy will be delivered from the electron beam to the RF. Okay, and next is you have the quasi-optical launcher, where the entire RF high power RF in a higher order mode is converted into the Gaussian-like mode, and the Gaussian-like beam is taken away from the launcher using a mirror system. So this mirror is a metallic mirror. Okay, and here your RF signal will be in a Gaussian mode, that is TEM00 mode. So you can use the reflection principles to take in this Gaussian beam out of this window. So the window generally they use is a either CVD diamond window, okay, or or they use boron nitride window. Okay, for a megawatt class of application, they will use CVD diamond window. And the spent electron beam, it will get collected in the collector region. Okay, so this is a schematic of the gyrotron, and this is the block diagram, means you can say the picture. Okay, here also you have the supporting magnetic coils are used so that your electron beam will get focused, and this magnet also responsible for the beam wave interaction. Okay, and this is the MIG, whereas this entire big setup is the collector region where the unspent electron beam is getting collected, and these are the mirrors where your RF signal is getting reflected and taken out of the window. So this is the RF window. So where these gyrotrons are generally used? So in a tokamak, that is especially in a thermonuclear fusion reactors, where you fuse two atoms to generate energy. Okay, so in that nuclear fusion reactors, we need to maintain the plasmas for a very large volume. Okay, so this is a core of the tokamak. So this shape, that is a D shape. So this is a core of the tokamak. If this core is of very large, then number of fusion reaction occur inside the core will be very large. Okay, but uh, why we can't increase the volume? We can't increase the volume because we have to maintain the plasma over that large volume. Means we have to confine the plasmas over the large volume. That is a main drawback. Okay, so if you want to confine the plasma over the large volume, you need to have a very large magnetic field. That is one cost requirement. And along with that, you need to heat the plasmas over that large volume. So for that, you need to apply the RF signal at certain frequencies. So all these requirements are there. So depending on the size of the core, your RF energy requirement varies, means their frequency requirement varies. So our Indian tokamak, that is SST1, that is Aditya tokamak, which is at IPR Gandhinagar. Okay, they uses 42 gigahertz gyrotron with a power level of 0.5 megawatt. Okay, whereas the ITER tokamak, that is International Thermonuclear Experimental Reactor tokamak, this is under construction at France. Okay, and they are expecting their power generation by 2030. Okay, so they uses 170 gigahertz. Okay, whereas the German tokamak 140 gigahertz heating systems are used. So how this frequencies are varied, because the core dimensions are different for all these different tokamaks. Our Aditya tokamak has some smaller core. Okay, so whereas the till now the experimentally carried out tokamak, this ITR, it has a very large core, whereas Aztecs U has somewhat a medium size core. Okay, so the proposal for commercial application of this fusion, they are proposed to develop the fusion reactors for commercial application, commercial electricity supply. So okay, for that they said their core dimensions will be very large, and the frequency requirement will be greater than 200 gigahertz. Okay, so this is the proposed core volume of the future nuclear tokamak, especially designed for commercialization of the nuclear fusion power. Okay, so they use the core volume of 2200 meter square. So for that very large volume, we need RF systems, heating systems with the frequency requirement of 200 gigahertz. Okay, so so for that we also need some additional supports also. So we will see those. Okay, so not only for the plasma heating we need RF power, we also need RF power for plasma startup, means how to start the plasmas. We also need RF power for operating the entire system at different experimental scenarios. We also need RF power at different frequency for plasma stability control, which means that we need RF power for various other requirements also. Okay, and that RF power frequency also slightly varies. If suppose in our IPR Gandhinagar, they not only uses 42 gigahertz gyrotron, they also uses 84 gigahertz and 110 gigahertz gyrotron for various other applications. Okay, like a plasma startup, they use 84, and they also use 110 gigahertz for understanding the entire tokamak setup in different scenarios. So it is not like your heating system is a single frequency. You also need a heating system that can deliver a 3-4 different frequencies. So in that scenario, what generally people do is, instead of installing 2-3 gyrotrons at different frequencies, they use a single gyrotron that can support all the 3 frequencies. So that's what generally people do. So that is a multi-frequency gyrotrons are generally proposed for a heating application, so that they can use it for multiple purposes. Similarly, if suppose in this future demonstration tokamak, they require the RF power of around 50 megawatt. Okay, so the 50 megawatt RF power is required, and to support this entire requirement, if our output power of a gyrotron is around 1 megawatt, okay, then we need at least 50 gyrotrons to support it. So if I increase the output power to around 1.5 megawatt or 2 megawatt, then I can reduce the number of gyrotron requirement very significantly, by which I can reduce the entire maintenance cost. So nowadays, the target is to have a source, microwave source, that can operate at multiple frequency and that can deliver the power of greater than 1 megawatt. Okay, around 2 megawatt it is targeted. So with this target only, we formulated this problem, that is design of coaxial cavity gyrotron for multi-frequency application, that is a 220, 251.5 to 83 gigahertz. Okay, and our targeted power level is 2 megawatt. So what our goal is, we need to develop a gyrotron system that can operate at all the three frequencies. Okay, and how we can change this frequency from 1 to 3 means by only changing the magnetic coil currents. Okay, by only changing the current in the coils and also by changing the potentials in the electron gun region. Okay, so what I mean is, I'm going to only change the current in this coil and I'm going to change the potential in this gun, so that I'm going to change the operation from one frequency to second, second to third. Okay, so my entire system is common. My entire everything is common. Only I'm tuning it electrically. Okay, only I'm tuning it electrically. So this is the challenging. Okay. So, and also we fix this frequency in such a way that it is above 200 gigahertz, so that they can be used for the futuristic commercial fusion reactors. Okay, so these are the requirements. So now coming to the challenge in the achieving high power, high frequency operation. So one of the major challenge in achieving the high power operation is we need to control the wall losses, because if you are operating the entire device at 2 megawatt, your ohmic wall loading will be very large. So what I mean is, your losses along the walls of the interaction cavity will be very large. So if you want to control the wall losses, what one step is, you can increase the radius of the interaction region by increasing the dimensions. Okay, which means that you need to operate the entire gyrotron at some higher order modes. Okay, so TE01 is a simple mode in a circular waveguide. Okay, whereas TE11 is a fundamental mode. TE01 is a circularly symmetric mode. Okay, that is a one of the lower order mode, and T02, 03, these are the lower order modes. So if you want to reduce the wall losses, because your output power is very large, so you will increase the volume and you will operate at higher order modes. So if you're operating at higher order modes, then automatically this mode competition will increase. Okay, so the mode competition will increase. And another one challenge is the voltage depression will also be large when you're operating at higher power. So what do you mean by voltage depression is, you are having an annular electron beam. Okay, so if you are having an annular electron beam, there will be a repulsive force between the two electrons. Okay, and which will reduce the potential of the electron beam. Suppose you apply a 85 kilovolt potential, the available potential will be around 80 or 79 kilovolt. So roughly your potential got depressed by 4 or 5 kilovolts. Okay, so that is also one major challenge. And this voltage depression problem increases with the increase in the beam voltage. Okay, so if you are operating at 100 kilovolt, then voltage depression will be very, very large. Okay, so that also has to be controlled. So the problem is, we need to control the mode competition, we need to control the voltage depression. So these are the two major problems in the design of megawatt class gyrotron. So these two problems can be overcome by using, instead of cylindrical cavity, you can use a coaxial cavity. So what coaxial cavity will do is, I will show. Okay, so what this insert will do is, it will reduce the mode completion, and it will also aids in reducing the voltage depression. Okay, so it will aid both of these ways. Okay, so that's why in this design we have used a coaxial cavity gyrotron where we have an insert. Okay, so this insert will travel from the electron gun and it will reach till the interaction region. Okay, so this is how. Okay, so now we will look at the flow chart of how we are proposing the design. So first is we need to choose the modes. Okay, that is a mode selection. Means which is the operating mode, and for the 3 different frequencies that we have to choose. Then we have to do the interaction cavity design. Then we should do the feasibility analysis, means whether our chosen modes at the design frequency is delivering the output power or not. That is feasibility analysis. Then we have to go with the input system design, that is electron gun system, magnetic guidance system. Then we have to design the output coupling system, means our launcher, RF window, and mirror system. So generally mirror will design first itself. Before starting off the design itself, they will design mirror, because sorry, RF window, because RF window is one of the costly part in the gyrotron design, because there they will use a CVD diamond window, which is a very costly affair. So once the frequency are fixed, they will design the RF window, then they will carry out all others. So these are the design goals and technical constraint. So our goal is we need to design a 3 frequency gyrotron. Okay, that is a multi-frequency gyrotron, and the output power is 2 megawatt, and the efficiency should be greater than 34%. And these are the magnetic coils that are currently available. Okay, means maximum we can go up to 12 Tesla. Okay, that is a maximum magnetic field that we can achieve. Okay, and others are in a ratio only. Okay, so the frequencies are generally chosen based on the application. Like for our case, we have chosen 220, 251.5, 283, all this chosen so that they can be used in futuristic this fusion tokamaks. Okay, and then we have to design the RF window to support the output coupling of these design frequencies. Then we have to design a mode selection. Then we have to go with the cold cavity simulation, then coupling coefficient calculation, then self-consistent single mode calculation. Means this self-consistent single mode calculation, time dependent multi-mode calculation, all these are feasibility analysis. Then we have to design the electron gun for that chosen beam parameters. Then we should also do the startup behavior studies, means whether the mode grows properly or not. So all the studies we have to carry out. So for this, we have used the design tool, like for mode selection, cold cavity calculation, coupling coefficient calculation, self-consistent single mode calculation. All this we have used the in-house tool, that is Gyrotron Design Suite. Okay, this time-dependent multimode calculation, startup studies, all these are carried out using self-T code. Okay, and this is a window of the software tool Gyrotron Design Suites. This is an in-house code tool developed at IIT Roorkee for carrying out the design studies of conventional and coaxial cavity gyrotron. And this tool was also benchmarked with some commercial tools like CST. Okay, so why we have used this particular tool is because when we are designing the gyrotron, we will operate at the modes like TE 4830 or 5534. So these are very higher order modes. If you carry out the PIC simulation for this much higher order modes, it is very impossible to run the simulation for a very long hours. So that is impossible. So that's why these tools are developed using analytical models, and we carry out these studies. So these are the different tools available in this entire suite. We can do mode selection procedures, starting current analysis, some initial magnetron injection gun calculation, and magnetic coil design, and interaction cavity geometry design, then cold cavity analysis, then the feasibility analysis, that is single mode analysis, multi-mode analysis. Then we can also do the initial calculation for the quasi-optical launcher, and we can also do RF window analysis, then the mirror synthesis, that is the mirror between the launcher and the output window, that also can be done using this gyrotron design suite. So this entire package was written in MATLAB, okay, and we can do both conventional and coaxial cavity designs through this. Okay, so I have written some very important equations. I didn't include other models. I have only incorporated only single mode analysis and multi-mode analysis for a very basic understanding. So in a gyrotron, in the interaction region, we will have an interaction between RF wave and beam and an electron beam. So these two has to interact. So which means that we have to solve the equation for the wave, and we have to solve the equation of the motion of the electron beam simultaneously, right? So the equation of the wave generally written as wave equation, okay, and where H is the auxiliary function to express T or TM mode in a transverse direction, right? So the CT is the transverse field component of electric field, whereas VMP is the field variation along the longitudinal direction. Okay, so if you solve it, you will get a Vlasov's equation, where right hand side is the source. Okay, so the source may be current density or charge density, but here we consider the current density JMP, that is current density of the electron beam. So ideology is we are having electron beam, and this electron beam, because of the random nature, it will generate the noise, and because of the noise there is excitement of the fields, and because of the resonant circuit behavior, only one particular frequency will get captured, and for that particular frequency the energy starts to deliver from the electron beam to the RF. So this is the brief working principle, right? So for that, this equation is the wave equation, that is a Vlasov's equation, and this equation is the force equation, F equal to EE, that is force equal to mass into acceleration. Okay, so that equation we have written. Okay, so E plus E V cross P. Okay, so whereas this d E divided by dt, so this is the rate of change of energy. Okay, this is the rate of change of energy. So if you solve these two equations, you will get a momentum equation, that is how the velocity of the electron beam varies as it travels along the path. Okay, so now we have to solve this equation, momentum equation and Vlasov's equation simultaneously to understand the behavior of the RF interaction. Okay. So if you want to understand the behavior of RF interaction in presence of several modes instead of assuming only one modes, then we have to solve the multimodal equation where this FMP corresponds to the presence of multi-modes, okay, not only the single modes. Okay, so by using these equations only, these single mode analysis and multimode analysis codes were written. Okay, so now coming to the mode selection. So once again. Okay, so coming to the mode selection, we need to choose the operating mode such that the interaction cavity dimensions are same for all the three modes. Okay, as well as the beam radius of offering the greater efficiency should be around slightly same. Okay, and our MCHI value. So the MCHI value is responsible for the output system design. So that also should be quite same. So we have chosen for this design as TE4830, TE5534, TE6238 as the operating mode, and the resonant frequency means for these resonant frequency, the beam radius to support a high efficient output is also slightly same. Okay. So look at the mode numbers 4830 and 5534. So all these are very higher order modes. Okay, so that's why I said we can't use the commercial tool like CST for carrying out this type of multimodal analysis. So which means that it is very difficult to run that kind of simulation in CST. So in the interaction design, what we are going to do is we are going to design the coaxial cavity. Okay, so the coaxial cavity has insert, and this cavity is open-ended cavity. You have a input taper, that is a down taper, along with a mid section, that is a straight mid section, and a up taper, the output up taper. So you have to design the three parts, and all these three parts are connected together. Okay, and for smoothing, they have used a parabolic smoothing. Okay, and this taper, there is a taper of this insert. Okay, the insert has some tapering. So we have to design these dimensions: the radius of the insert, the radius of the cavity, and the tapering, and everything we have to design. And our design should work for all the three frequencies. That is very important. Our design of this cavity should support all the three frequencies. So the resonant frequency of this cavity should be matched with the design frequencies, that is 220, 251.5, 283. So that we have to take care. So in this design, we have used a triangular corrugated insert in the coaxial cavity. So why we go for a triangular corrugated insert is because compared to rectangular corrugated insert, triangular corrugated insert offers much advantage in ohmic wall loading. So this ohmic wall loading in outer cavity can be managed, but the insert, because your insert is like this, now cooling of this insert is very difficult. So we have used a triangular corrugated insert over a rectangular corrugated insert. So that is the one point. And this is the first other than rectangular corrugation, this is triangular corrugations was proposed by our group at IIT Roorkee, and this design is the first ever design carry out using a triangular corrugated insert. Other designs of coaxial cavity gyrotrons are carried out only using a rectangular corrugated insert. And the advantage of triangular, it also offers a mode rarefaction along with the ohmic wall loading controlling. So next is we have to check the eigenvalue analysis, means whether our interaction cavity supports this chosen modes, and with this eigenvalue curve only we will decide the radius of the insert. So generally in designing the interaction cavity, we will design the outer cavity radius using the mode number. Then insert radius is defined based on the slope of this eigenvalue curve. Okay, so what do you mean by that? So if the curve, this curve slope is very sharp, okay, if your slope is very large, then the diffractive quality factor of the cavity will be very large, okay, will be very large. And if it is straight, then there won't be any change in the diffractive quality factor. If it is an increasing, then there will be a poor diffractive quality factor. So we need somewhat moderate diffractive quality factor, and also we need our operating mode should be in a positive region. Okay, means our operating mode line should be in a straight region, whereas our other competing mode should be in a negative slope region. Okay, so the negative slope region should be maintained for competing modes, and the straight region should be maintained for a desired mode. Okay, so we have to choose the C in such a way. Okay, so for this design we have choose C something around 3.7, so that the operating mode will be in a flat region, whereas the competing modes in a negative slope region. So in that way we can control the mode competition. Okay, so this is the eigenvalue curve for 283 gigahertz operation, that is TE 62,38. So these are the interaction cavity dimensions, that is L1, L2, L3, that is length of the down taper, then straight mid section and up taper. And there is a parabolic rounding with diameter D1 and D2 equal to 4 mm, and the angle of down taper and up taper are 3.5 to 3.0 degrees. Okay, and these dimensions, radius of the insert, they are taken from this eigenvalue curve. So we have fixed around 3.75. So the C will be 3.75. So Ri will be 3.75, means R0 divided by 3.75. That is the Ri. Okay, R0 divided by C will be the Ri, and number of slots also fixed. Okay, also fixed, so that we can have this losses very less. Okay, so the number of slots also fixed, and the spacing of the slots also determines this losses. Okay, so that also has to be fixed. So by that we have fixed this entire interaction cavity geometry. So now after this we have to check. Okay, so after that we have to check whether after that we have to check whether our interaction region offers the support to our chosen modes or not. That you have to do it by using the cold cavity analysis. Means you have to solve only the wave equation without the right hand side, and you have to check whether the RF field is forming a Gaussian profile or not. That we have to check. And in this we have we have determined the diffractive quality factor of all the three chosen modes, and we have also checked the resonant frequencies. Okay, because our resonant frequency of this interaction cavity at the chosen mode should match with the desired frequency. So that also we have to check it. So that we have done, and it shows that at the resonant frequency, the RF field, this is the electric field profile, is maximum. Okay, is maximum at the center of the interaction region, where the RF electric field is maximum. So which means that the interaction will be efficient at the center of the interaction region. Okay, so that we have done. Then after that we have to look into the mode competition studies. Means as I said, there are this RF energy initiates from the noise. Okay, so noise means you have a multiple frequencies, and your RF circuit should capture one of the resonant frequency. Okay, so now what will happen, your RF circuit can also catch some other mode, which is not our desired. It can also catch some other mode, and it can also operate at some other frequency. That means that if you design at 4830, it can also sometimes it can also catch some other mode like 4631 or some other. Okay, so that we have to study. Okay, so for that we have solved the coupling coefficient for the beam radius of maximum efficiency. So for this beam radius, for this 4830 mode offers a very maximum coupling. Okay, so that we have calculated, that is QDCC, that is diffractive quality factor times coupling coefficient. So this should be maximum for our desired operating mode, and for our remaining modes it should be very less. So if you look at for 220 gigahertz, the coupling coefficient is very better, whereas for 251 the coupling coefficient is slightly not better, because other competing modes are also contributing. Whereas for 283 gigahertz also, there are lots of competing modes very close to the desired modes. Why? Because is our cavity dimensions are chosen such that for this 4830, if you choose 3.75, most of the competing modes are lying in a slopy regions, negative slope regions, whereas for other higher order modes, they are in a straight regions. Means the more rarefaction is better for 220 compared to other modes. Okay, this happens in all multi-frequency cases. In all the multi-frequency cases, either our design promotes one frequency, and it can't offer the same amount of efficiency to other modes. Okay, so this will happen in all multi-frequency design. Okay, so in our design, 220 gigahertz efficiency will be very good compared to other 251 or 283 gigahertz. Okay, so this is the mode completion study for 283 gigahertz. Okay, so next is feasibility analysis. One second. Sorry, I connected the charger. So next is feasibility analysis. So in that, we have to check whether our output power is achieved at a desired value, and also we have to check the beam parameters so as to achieve this amount of output power. So this feasibility analysis, we have solved both Vlasov's equation and momentum equation, that is dP by dz equation. And in this analysis, if you look at the power output can be obtained at 2 megawatt for all the three chosen modes, and the efficiency is also around 35%. So look at this. As I said, our 220 gigahertz is most efficient because their mode rarefaction is also very much better. And we have chosen the beam parameters in such a way that it can offer the power for all the three modes. And the ohmic wall loading, is also determined. That is how much the losses offered on outer cavity on the insert, that also are calculated. So this is about single mode analysis. Means we have considered only one operating mode, our desired mode, and we have solved the losses equation. That is this equation. This is the losses momentum equation, and this is losses equation. So we have used single mode equation, whereas for multimode analysis we have to use this equation and solve the problem. That is, this MP values changes. That is a multimode calculation. And in this equation, this is a time dependent equation where as the time varies, this modal function also going to vary. Right. So this is, we have to solve the multimode analysis. Okay. So if you look at this figure, we have considered multiple modes of most of the competing modes for 220 gigahertz operation. So if you look at this, the beam voltage in this calculation varies from 50 kilovolt to 87 kilovolt over a time period of 2500 nanosecond. And the magnetic field, alpha, beam current, all are kept at the desired values. Okay. So if you look at this, as the time progresses, initially the output power was in the mode 4831. Okay. And as the time slowly progresses, when the beam voltage reaches around 85 around, our desired mode starts to grow. Okay, our desired mode starts to grow, and after 2500 nanosecond, the beam voltage kept constant at 87 kilovolt. So our desired mode continues. Okay, our desired mode continues even after 500 nanoseconds of constant power. Okay, constant signal. So this conveys that yes, there is a chance of output at 4830 mode, T4830 mode at 220 gigahertz. So by this analysis only, we said that okay, it is feasible that at this 4830 the power output is feasible and it will remain stable, because feasibility is not only that mode excitement, it also that the mode should remain in that particular power level for a longer period of time. Means if you supply the beam voltage at the desired beam voltage for some time, then it should remain stable. But in some cases, what will happen, this mode after a period of time, the another mode starts to dominate. Okay, so that also happened. That also we have checked. Yes, up to 500 nanosecond, there is no chance of other mode to excite in this setup. Okay, so next is in this figure, you should also note that there is a power output in 4831 minus, which is around 10 kilovolt. So we can't suppress this power below 10 kilovolt. If you suppress this below 10 kilowatts, then what will happen is your output power will also reduces. Okay, so this is a kind of trademark we have to make it. If you want a higher output power like around 2 megawatt, then there will be some amount of power will waste at some competing modes. Okay, so if you look at the gyrotrons, that is conventional cavity gyrotron, this problem won't happen. But in coaxial, this peculiar problem comes where there is some significant amount of power will be going to the competing modes. Okay, there are two ways you can overcome it. One is if you use a very low diffractive quality factor, then you can overcome it. But ultimately what will happen is your output efficiency will reduce. So it is like you can only manage this problem, you can't rectify it complete way. Okay, that's what our understanding of this tells us. So even though we have solved a lot of ways to resolve it, but ultimately we found that okay, this is the bottleneck, we have to accept it. So in the same way, we have done the multimodal analysis for 251.5 gigahertz operation, where the power we got it for TE 5534 mode. Okay. So in this, if you look at the figure, initially the power will be in a TE 5535 minus, whereas after a certain period of time, then our desired mode starts to dominate over others and it will remain stable. Okay. And in this figure also, there is a slight amount of power available in around 10 kilowatt power available in 5535 minus, right? So this is a multimodal calculation carried out for TE 6238. Okay, so at 283 gigahertz operation. So as you look into the figure, there is growth in a power of the desired mode, and it remains stable, So after this calculation, we finalized that okay, the power is now available at all the three chosen frequencies, and we have chosen the beam parameters in such a way that so now we have to supply these beam parameters through electron gun, that is a magnetron injection gun, which supplies the electron beam with a desired value of beam voltage, with a desired value of beam current, with a desired value of velocity ratio, and the magnetic field, external magnetic field. So this alpha, so alpha is nothing but a velocity ratio, which is telling us the ratio of transverse voltage to, sorry, transverse velocity to the longitudinal velocity. Means the electron beam in a gyrotron, it will travel in a cycloidal path. So the energy which is present in the transverse velocity is taken care of this interaction, whereas the longitudinal velocity is not responsible for the beam wave interaction. So always this alpha should be greater than 1 for the gyrotron. That is for even for conventional or coaxial, this is the rule. Okay, so this is how the electron annular electron beam will be created, and it will rotate by itself and it will travel forward. Okay, it will rotate by itself and it will travel forward. That is, it travels in a cycloidal path. And in this design, we have used triode type of electron gun. That is, you have cathode, you have modulating anode, and you have anode. Okay, and you will also have an inset that is connected at the cathode region. So inset from this point, it will start and it will go till the interaction region. So this region I have exaggerated in this. So now what the challenge is, we should achieve the beam parameter for all the three operations by using the same gun, by using a single gun. And our choices, we have to, excuse me, and the choice available with us is we have to use the available magnetic field, and we can change the currents in the coil so as to achieve the required beam output. Okay. So we have done this calculation using the code 2D tool, 2D particle trajectory code called ESRI. Okay, and in this, if you look at the length of the coil, radius of the coil, breadth of the coil, number of turns, all are fixed for all the three frequencies. Okay, and only the current in the coils I'm going to change. Only the current in these coils, magnetic coils, we are going to change, and we are going to achieve a desired magnetic field profile. And with this desired magnetic field profile, our output beam values will also change. So this is the idea. So our beam trajectory will form in this way. So this is the coaxial insert. Okay, and if you enlarge it, there is a slight gap between the insert and the beam region. Okay, so if you look at the output, we can achieve the desired beam parameters by varying the currents in the coil and also the potential of the cathodes and the modulating anode and the anode. Okay, so that we have carried out. So next, once the input system design is over, next we have to consider the output system. So as I already said, the output RF means this RF window was already designed. So only point to be designed is our quasi-optical launcher. So now quasi-optical launcher, how we are going to design is, we have to design a launcher so that it can support all the three modes at three different frequencies. Okay, So this launcher is a corrugated waveguide. Okay, so corrugated waveguide is something where the inner walls are not so smooth. Because of this corrugations, what will happen? Your mode, that is a TEMN mode, will convert into the mixture of the modes. Okay, then that mixture will get combined and it will form a Gaussian like mode. Okay, so we have to design this waveguide corrugations, okay, inside corrugations in such a way that it converts the higher order modes, that is the 48, 30 modes, into a Gaussian like modes. Okay, that we have to design. All right, so in this entire design, we have carried out these designs using the launcher optimization tool, that is a commercial tool, and we have carried out this. And these are the launcher length, launcher cut length, radius of this launcher, and taper angle. Okay, and the output Gaussian content is around 95% in all the three cases, is greater than 95% in all the three cases. So this figure shows the electric field intensity along the this launcher. Okay, so along this launcher, if you look at the electric field intensity, so along the cut, along this launcher cut, the field intensity is so large so that you can take the entire Gaussian beam out of this launcher. And we will also keep the mirrors at this launcher walls so that it can reflect it and it can take the power out of the launcher. So we also checked what will be the field intensity at the launcher cut and at the possible location of the first mirror. So it shows that yes, the field intensity at these locations are approximately same. Okay, so the location of the maximum field intensity of all the three frequencies are approximately same. So which means that you can use the same mirror system for the output transfers. So with this, we have entirely concluded the design of the entire multi-frequency gyrotron. So along with this design, we have also carried out one more analysis, that to understand whether our design is sufficient for a practical development, because in practical we have some other problems. Okay, that also we have understood. And what one problem generally in coaxial design faces is the misalignment. Means your coaxial insert won't be at center, there will be a slight misalignment. But however, till now there is no analysis available to calibrate how much misalignment is allowed and how much is accepted. This calibration we have carried out. What we have done is we have taken the equations of an ideal system. Okay, ideal system. Then we have incorporated the misalignment. Okay, we have incorporated this misalignment in this equation. So the single mode linear equation of the dispersion changes into the multimodal equation, because if you incorporate this misalignment, then we will have to use this Graff's addition theorem. Then our entire dispersion relation becomes a multimodal equation. Okay, so now solve this multimodal equation is very difficult. Solving this multimodal equation is very difficult, and we have to use the matrix algebra. Then we have to solve it. Okay, so after solving, we have to use again, we have to solve the momentum equation. we have to solve the wave equation, and we have to determine whether the power and efficiency changes are there or not. That we have to look at. So that we have carried out. We found that at 220 gigahertz, if there is a misalignment, even of 150 micrometers, then the output power will falls off and efficiency will falls off. But what importantly, at even at 150 micrometer of misalignment, uh, the input insert ohmic wall loading is very large. So insert ohmic wall loading increases exponentially with the misalignment. So this is one of the important thing to be noted. Okay, so that we have carried out, and yes, we have concluded this problem. And what are the conclusions? So overall, my thesis, the research work contributes to the design of some major components of the coaxial cavity gyrotron to support dual and multi-frequency operation, especially interaction region, uh, especially interaction region and electron gun design. We have also carried out output system design, and this gyrotron can be used for futuristic tokamak applications. Okay,
Sir,
so
take out 44 page number, sir.
hello,
Hello.
yes sir.
Participants, please unmute your mic. Participants, please, all of you mute your mic. Okay, sir, you can continue.
Yes, thank you. So what is the conclusion is next generation, we look beyond 60 gigahertz. Okay, and our millimeter and terahertz wave requirements is keep on increasing, and there are very lots of uh, development occurring in a vacuum electron sources, especially due to the advancement in machinings. So there are lots of scopes that are occurring in millimeter and terahertz wave regimes, and in future this vacuum electron sources will be a very competitive with the solid state devices, even for the commercial applications. As yes, for high power they are the champions, they always remain. So this is the general conclusion. And what is the some futuristic work? This is one of the futuristic work. So gyrotrons, they are not only used for hyper application, they are used for low power applications, especially in DNP NMR experiments. So we are now working on to design these gyrotrons for low power applications. But what advantage we have is at low power is we can design these gyrotrons not with the requirement of very large magnetic field. Since the output power is very small, we can operate this gyrotron at second harmonic or some higher harmonics. So what this makes is you can use the same gyrotron at very low magnetic field requirements, but we have to check the efficiency and other things that lots of research are going on around this area. So we are also working related to this. So these are our current research interest. So yeah, so thank you. I conclude this, and I thank Professor Ramakrishnan for giving me this opportunity, and I thank all other committee members for approving this talk. Thank you so much. So I request participants to ask some queries.
Hello, participants. If you have any queries, you can ask Dr. Yuvraj. Hello, Dr. Yuvraj sir.
Yes, sir.
Can
Yes,
you
please.
can you please explore some new research areas in the field of millimeter liquids?
Yes, sir. So, as I said, this before 2010, everyone looks for high power only for vacuum electron devices. But nowadays, this vacuum electron devices, there are lots of researches going on for low power application, especially 20 watt, 40 watt. So these applications, vacuum electron devices, are they are targeting, but the frequency requirement is very large. Okay, around 200 gigahertz they are working. Main problem is you have to design the interaction circuit. You have to design the interaction circuit. That interaction circuit should be very efficient interaction circuit, because at meter and terahertz regime, your circuit will be so much tiny. So in the tiny, you will send a very small electron beam which will deliver its energy. Okay, so you have to reduce the dimension, and also you have to increase the efficiency. So that is a challenging. So many people nowadays, they are working on the design of this very tiny structures, interaction structures for TWT, for backward wave oscillators, and all these works are going on. And I also read some TWTs. For TWT, they are using periodic structures. Okay, some kind of periodic structures. So these research activities are currently going on in this domain.
Okay, sir. Participants, if you have any doubts, you can ask.
Sir, what are the advantages of using dual or multi-frequency operation in a gyrotron?
Yeah. So that is okay. So as you look at this figure, so you need a RF system for various applications, like not only for heating the plasmas, we also required RF system for plasma control or to start the plasmas. So all this require RF, but the frequency requirement are different. Okay, for example, even our Indian tokamak, we use 42 gigahertz gyrotron for heating, 84 gigahertz gyrotron for plasma startup, and 110 gigahertz for operating the entire tokamak at a different experimental scenario. Right. So uh, instead of purchasing 3 gyrotrons at 3 different frequencies, people nowadays prefer to go for a multi-frequency gyrotron, because we can have only one system, and we can solve all the 3 purposes. That is the one advantage.
Thank you, sir.
Yeah, thank you.
Okay, participants, if you don't have any further doubts or clarification, we will wind up this session. Thank you, Yuvraj sir.
Yeah, thank you so much, sir. Thank you so much.
We are very happy to be. Hello.
Yes, sir. You are audible.
Hello. We are very happy as you share your valuable time with us. Particularly this particular induction program is particularly about millimeter waves. So we would like to have planned sessions exclusively with the people who are working or who are having this experience in this area. So we are very much thankful to you, sir, for sparing your valuable time. Thank you very much. So participants, the session is over, and tomorrow we will meet at 9:45 a.m. Thank you all.
Thank you so much, sir. Thanks
Thanks.
for giving me the opportunity and giving me the platform to share my research activities, which I carried out at IIT Roorkee, and also now I am carrying out at NIT Andhra Pradesh. So it is a very nice opportunity for me to tell about my research activities. So thank you so much. and I look forward for future collaborations and everything with you.
Sure.
Thank you so much, sir.
Sure. Thank you very much.
So shall I close the session, sir? Shall I leave?
Yes, sir. You can close the session. You can leave the session.
Okay, sir.
Participants, you can join the meeting tomorrow with the same link, and I request you all to join by 9:45 a.m. Professor L. Anjaneyulu will be the speaker for tomorrow's 2 sessions. We will be giving lectures on millimeter wave systems and other related areas. Thank you all. Now you can